Hello, good morning, everyone. Let's start the class a little bit early today. So this week we are supposed to talk about set, but we don't have a lot of difficult things that we have taught last time. So instead, I will talk about something that is related. So when we talk about set, we have defined uncountable and countable sets. So what is meant by countable set? So countable sets are sets such that the total number of items inside, they are either finite or when it is infinite, we can make a one-to-one correspondence with the integers in the natural number set. So in other words, if it is a countable set, we can have a way to count out the items in the set one by one without missing. On the other hand, we have also given an example of an uncountable set, which is the set of real numbers. It turns out that the number of items inside the set of real numbers, it is much more than the number of items in the natural number set. There is no way that we can form a one-to-one correspondence between the items in the two sets. In other words, the real number set cannot be counted, so it is an uncountable set. When we are proving that it is uncountable, we have made use of a technique called diagonalization method or a diagonal method. It turns out that this technique can be used in somewhere else, and this is the topic for today. Okay, so we want to talk about a very famous problem in computer science called the halting problem. I will define the problem later, but let's see the introduction. First of all, if we have studied programming, we will see that some programs will stop after some number of steps. For instance, let's say this is a very small program. This small program reads an input value x and just print out the value x. So in that sense, this program will actually stop after two steps, after running this line and then after running this line. So this program will stop. On the other hand, let us take an example of another program. Okay, so this is another program. This time, it reads an input x, but then we have a while loop. While loop checks the condition here. Whenever it is something that is true, we will go back again and again until it is not true. But in this example, we specify something that is inside is always true. So in that sense, when we enter this so-called while loop, we will perform this step again and again and again forever. So although it looks like it will print out x in the end, but then it will never escape this while loop. So this program will run forever. So we will say that this program enters an infinite loop. So there is a looping here and it runs infinitely. So in computer science, people always wonder whether it is possible to have a program P that can check for any other program, let's say Q with some input D, whether this program Q will stop on the input D. So what does that mean? So we want to find out whether there is a program P so that it will read the code of Q. It will read also the input of D, okay, so that it checks whether Q will stop on D. If Q will stop on D, then the program P will tell us yes. Otherwise, it will tell us no. And this is the so-called halting problem. So halt means stop. Whether we can have a program P that checks or that decides whether another program Q will stop on input D or not. And the question here is, does such program P exist? Of course, we require such a program should stop infinite number of steps on every code Q and every input D. Otherwise, it is pointless. Otherwise, we just let Q to run on D and wait until whether it stops or not. So we want to have a certain program P that after reading Q and D, so that after reading Q and D, using a number of steps, it can tell definitely whether Q will stop on D or not. Gives us an answer yes or no. What we are going to show today here is such a program P cannot exist, and then we want to show this by contradiction. The proof actually is a diagonal proof. So we are now going to show this by show P cannot exist by contradiction. So from now, let us assume to the contrary that such a program P exists and see what will happen. So we now assume that such a program P exists. What we can do is we make use of P to construct some other program G. This program G will assume some input code Q that it reads in. Let us take a look of how G works. So this part is the program G. So the program G will read the code of Q and do the following. Yeah, because P exists, so what G does is G will call P and then checks whether if the code Q, the program Q runs with the input Q. So notice that these two are now the same. We just have the input code Q so that we can make use of Q to represent the program and also represent some input data. So G will first run P, assuming that it reads the input code Q and with the data Q. So P will check whether Q will stop running on the input data Q or not. So if P answers yes, then what will happen? Then this program G will enter into the infinite loop, just like what we have seen in the first few pages. So if P answers yes, then G will have a while loop, while true, whatever, x is equal to x plus 1. On the other hand, if P answers no, then in that case, G will stop running. Okay, so P answers yes means that Q will stop on Q. P answers no means that Q will not stop on Q. Okay, so it is quite strange. So we will see why we are designing G like this. But first, we want to emphasize that if P really exists, then G is well defined. If P exists, then we can ask some of our friend or God to write the program G for us. So G is there. But on the other hand, let us check what will happen when G runs on input G. Okay, if G runs on the code of G, what will happen? Okay, let's see. Okay, so we are having only two cases. Either G stops running on input G or G won't stop on input G. There are just two cases to consider. If G stops running on input G, so G will stop running on input G. So in that case, when running P on G with input G, P will correctly tell us that it will stop running. So it will answer yes. But in that case, what will happen to G? G will enter into an infinite loop. So what does that mean? So when G stops on input G, then G, given the input G, although we say that it will stop, but then G will enter an infinite loop. So there is a contradiction. When G runs on G, if it was supposed to stop, then it will go on forever. So there is a contradiction. Similarly, what happens if G won't stop on input G? Now, if G won't stop on input G, then what will happen? In that case, because P can check this line in finite number of steps, so in that case, after finite number of steps, P will answer no. And in that case, we will enter this line, and then G will stop running after that. So if G won't stop on input G, then G will stop running. So we will also get a contradiction, right? So whenever G is given an input on G, whether it will stop running or whether it won't stop running, both cases will lead to a contradiction. So what does that mean? So that means that G cannot exist. Okay, so if we look at it carefully, this proof is actually a diagonal proof. Where is the diagonal? Okay, so what we have just constructed is a program G that cannot be equal to any other program Q. The reason is that G and Q will behave differently. Whenever Q stops running on Q, G won't stop running on G. Whenever Q won't stop running on Q, G will stop running on G. So in that case, G cannot be Q. G cannot be equal to any other program. So G does not exist. If G does not exist, then P does not exist. We are using what? The modus tollens, right? If G does not exist, then P does not exist. So in that case, we're done. Okay, I think that's all for what I want to show you today. It is really something that is hard, but I hope you can understand what I'm talking about. So let me check if you have any questions. Okay, yeah, I hope you like it. So this is really something that is hard. And then, yeah, so don't worry if you need to revisit again and again, or you can go to the web and check for other people's discussion or explanation of what is meant by the halting problem. Okay, thanks all for today, and then thank you. Thanks all for coming, and then we will meet again on Wednesday. Okay, see you.